Hello, we are Group 21 and our project is Smart Safe.
Our team members are
Eric, electrical engineering major.
Nick, computer engineering major.
myself, Alexis, electrical engineering major, and Lakshmi, our computer engineering major. As monitoring's one environment become increasingly important, ensuring the security of personal belongings is essential in today's world. Our project aims to address this need by providing a reliable and secure storage for consumers, offering a portable and compact environment to keep belongings and valuables protected. It will include features like real-time alerts about unauthorized access attempts or tampering, which will provide users with immediate awareness and a peace of mind. Create keyless instant access with convenient keypad entry and biometric fingerprint scanning technology. Our motivation is to build a safe that not only safeguards valuables, but also provide an awareness of its security status, customize additional access levels, and monitor usage remotely through email notifications. The basic goals of our design is for the safe to unlock when the correct passcode is entered and remain locked if an incorrect passcode is entered. The safe should also unlock when it recognizes a registered fingerprint and remain locked if it reads an unregistered fingerprint. The system should display readable user prompts during the safe's operation and also send email notifications to inform the user when the safe is being accessed. Our advanced goals include providing a web interface for registered users to enter their email for notifications, incorporating a battery backup system to maintain operation during power outages, and implementing a motion sensor to detect individuals near the safe. Include lights and sounds as visuals and audible indicators of the safe's locked or unlocked status. Additionally, the safe will enter a lockdown mode after 3 incorrect passcode attempts. As stretch goals, we envision tamper detection to alert users of unauthorized breach attempts, a temperature sensor to monitor if your safe temperature exceeds a predetermined range, and an email reminder system for users who forget to close the door.
Here are our engineering requirements and specifications that we laid out for this project. One of our main access points is the fingerprint reader, so we wanted it to have an average 90% accuracy. This is to account for any potential fingerprint read errors. For our motion sensor, we wanted it to be able to sense movement and send a signal from at least 6 inches based on our design. We also set the LED accuracy to 90% for potential breaks. We decided to set the email notification receival to be under 1 minute 95% of the time, our lockdown mode activation to occur after 4 passcode attempts, our self-lock feature to occur after 30 seconds, and our safe to be 18 inches in length, 10 inches wide, and 10 inches tall.
Here is a high-level block diagram of our Smart Safes hardware system. We have our MCU sending signals to our buzzer, LED, display, website, and email server, and our MCU receiving signals from our keypad, motion sensor, and door sensor, all while receiving power from our regulators.
Here's our software block diagram and flowchart. To start, when a user attempts to access the safe, the motion sensor will be triggered and the safe will send a notification to the owner about motion detection. From there, a user who has their fingerprint registered would be able to access the safe and the door would unlock and portray that with a green LED and a buzzer sound when scanning their finger. The owner would also receive a notification about the safe being unlocked. But after being unlocked, the safe will self-lock after 30 seconds, whether the door is closed or not. Somebody who tries to access the safe and is not registered with their fingerprint will receive a red LED and buzzer noise. A user who has not registered their fingerprint will need a passcode from the owner to enroll their fingerprint, or they will have to use the keypad to access it. With the correct passcode, the safe will unlock and do the same protocol as the fingerprint with a valid attempt. After the 4th failed attempt on the keypad, the red LED will flash 3 times and the buzzer will sound for 5 seconds, initiating lockdown mode, where the owner gets a notification for failed attempted entry, and the keypad will be locked out of use for 30 minutes, or until a registered user uses their fingerprint to access the safe, which will deactivate lockdown mode and unlock the door. Our door sensor is a failsafe in case an intruder tries to break open the safe, since the safe will send the owner notification that it was broken into. Here's a block diagram of our keypad functionality. From startup, the user is greeted with a home screen prompting them to input a passcode or use their fingerprint. If the user types in a passcode for both cases in which the safe access is granted or denied, both return to the home screen after confirming the input with pound. In addition to keypad access, we also have an enroll fingerprint mode, reset passcode mode, and return to home button. From the home screen, if the user presses A, they will be prompted to enter a master code to continue. If the master code is correct, they will be given prompts to enroll their finger. If the passcode is wrong, they will return to the home screen. If the user presses B, they will also be prompted to enter a master code to continue the process. If correct, they will be given prompts to reset the passcode. If incorrect, they will return to the home screen as well. The return to home button was implemented in all modes, so if the user wishes to not continue any process, they can press D at any time to return to the home screen. Here are a couple pictures of our final safe design. In the top left, we have all of our components implemented into the door. To the top right, we have all of our PCBs connected and power flowing through them. On the bottom left, we have the safe being designed, and on the bottom right we have the back of the safe and the power cord connected to the back.
For choosing our microcontroller while also considering using a microprocessor, we compared the Arduino Mega 2560 Rev 3, the Raspberry Pi 3 Model B+, and the ESP Room 32. We went with the ESP Room 32 due to its affordability, processor speed, and it having a decent amount of pins for our peripherals. It also has its own built-in web surfer, which is important for our smart safe.
In this slide, we will be comparing our keypad selection. The three different types of keypads we will be comparing is membrane, mechanical, and touch sensor. We decided to choose the membrane keypad because it is user-friendly, easy to maintain, and requires minimal space and weight, which is suitable for our safe design. Our final decision for our part selection is the Nextion 16 keys matrix keypad module, which is shown in the picture below.
For our fingerprint sensor selection, we compared three different types of fingerprint scanners: capacitive, which uses the pressure of the fingerprint; optical, which uses the light of the fingerprint; and thermal, which uses the heat pattern of the fingerprint. We chose the optical fingerprint sensor because of its reliability, fast accuracy, and suitability for a variety of skin conditions like scars. For our part selection, we picked Hangzhou's Tech Grow R307 fingerprint module, which is shown below. For our lock mechanism selection, we compared three different types of actuators: in linear actuator, which converts rotational motion into linear motion using an AC or DC motor; stepper motor, which converts electricity pulses into rotation motion by a fixed number of degrees; and solenoid, which converts electrical current into linear motion using electromagnetism. We chose the solenoid due to its quicker response time and lower power consumption while providing the same benefits as the other two. For our part selection, we chose the UXcells 1240L. since it offers the longest operational duration and largest size, providing a more secure and reliable operation for our design.
For our motion sensor selection, we decided to use an ultrasonic sensor since it does a great job at sensing movement. We considered the HC-SR04, the URM37V5, or the TCT40 for our sensors. In the end, we decided to go with the HC-SR04 because many of us have had experience working with it before, it met our pin requirement, and it did cost the least if there was a case where we needed to buy more. For our display selection, we first had to decide if we wanted an LCD, LED, or an OLED display, and we narrowed it down to LCD or OLED. From those types, we considered the LCD 1602 module, the ESP32 touchscreen 2.8-inch LCD display, or the HiLetGo 2.42-inch SSD 1309 OLED. And after buying and testing them all, we decided to go with the SSD 1309 OLED because the output was easily readable. It met our PIT requirement. It has Arduino libraries for setup. It runs with I2C, and the overall look fits into our design very well. For our magnetic door sensor, we had to consider what type of switch we wanted to use for our door, and we landed on using a NC or normally closed switch since the door will remain closed, and once it opens without registered access, then it trips and sends a signal. From there, we considered the Gebeldet NO/NC magnetic switch, the Gagalar heavy-duty wired alarm NC, and the Victorsholm magnetic reed switch NC. We ultimately chose the Gebeldet switch since it carries both NC and NO switches in case we decided to change how the door functioned, and the color fit our design more than the Victorsholm switch, even though it costs less.
Since we're using an uninterruptible power source to supply power to our safe, they use different batteries to power its backup system. For our battery selection, we compared two different types: alkaline, which converts chemical energy into electrical energy through a chemical reaction, and lithium, which converts movement of lithium ions into electrical energy. We chose lithium batteries due to its higher energy capacity, longer lifespan both in storage or during use, and a wider temperature range compared to alkaline batteries. While all three products we compared offered similar features, we picked Integral Mini UPS battery backup.
In this slide, we compare the benefits and drawbacks of linear regulators and switching regulators to see which suits our project's needs best. We decided on using linear regulators due to their simplicity, affordability, low output voltage, and low noise. For our voltage regulator selection, we compared the LD1117, the HT7333, the AMS1117, and the LM7805 to see which was best. We chose the AMS1117 due to its affordability and high output current, and we chose the LM7805 due to affordability and familiarity.
For our relay selection, we compared two different types: electromechanical, which uses electrical and mechanical mechanisms, and solid state, which uses only electrical mechanisms. We chose the electrical and mechanical relays due to its high current and voltage ratings, thermal management, and popularity. For our part selection, we picked the Songlys Relays SRD05VDC. Due to its newer technology, proven reliability, and popularity, all three have similar specifications, but this relay has many resources available for troubleshooting and support, which can help minimize the risk of potential downtime and enable faster iterations to our circuit, since relays are known to require more frequent replacements compared to our other components.
For choosing our buzzer, after comparing the electromagnetic, magnetic, and piezo buzzer, we went with the magnetic buzzer due to its operating voltage being compatible with our microcontroller and its affordability when buying them in bulk. For choosing our LED, after comparing the common anode LED, common cathode LED, and the RGB LED module, we went with the module due to its affordability, the fact that it has built-in resistors, and that it has an online guide on how to use it with our ESP Room 32.
For our website technology, we initially had to decide if we wanted to develop a whole separate database for the data, but we realized if we store all our data on the ESP32, it'll be more secure. So we decided we were going to have the notifications be sent out from the ESP32 web server directly from the ESP32. From what we found, we considered the ESP32 web server, the ESP32 async web server, and the MicroPython with UASync IO. We concluded on the ESP async web server because we found that the libraries associated would help us with real-time applications and IoT or Internet of Things dashboard setup. Also, the only info that is transmitted currently is the email address entered by the safe owner, so traffic shouldn't be a problem.
In this slide, we will discuss email protocol and library selection. The three different email protocols we will compare is SMTP, POP3, and IMAP. We chose SMTP because it is typically used to send outgoing emails, and it is easy to implement and can be used with any service provider. For our email library selection, we chose ESP Mail Client Library, which is specifically designed for the ESP32 microcontroller and can be used with the SMTP protocol. Three different email service platforms we will be comparing is Gmail, Outlook, and Yahoo. We chose Gmail as our primary email service platform for users to receive email notifications about their safe because it is user-friendly and a reliable email service. It also comes with enhanced security protocols like TLS and email authentication. For our service provider, we chose Gmail SMTP because it works well with the Gmail service platform and provides efficient email delivery. For our software program selection, we will be comparing Visual Studio Code, Code Composer Studio, Platform IO, and Arduino IDE. We chose Arduino IDE as our primary platform because it works well with the ESP32 microcontroller and provides an easy-to-use environment with real-time testing. For our hardware selection, we will be comparing Eagle PCB, KiCad, and Fusion 360. We chose Fusion 360 because it is user-friendly and provides special features to help design our PCB layout.
Alright, here's our main PCB. This board contains our ESP Room32 that will deliver power and handle communication for our peripherals. Each set of pin headers is reserved for a specific component, including a GPIO pin that plays a part in the operation of our locking mechanism.
Our second PCB is exclusively for our locking mechanism. We're using a power barrel jack to supply 9 volts to our design, as required by the solenoid. A 5-volt regulator is included to power the 5-volt relay in the main PCB. To reduce noise, we added 2 capacitors to the voltage regulator. Additionally, LEDs were incorporated to provide power status indicators for both the 9 volts and 5 volts components. The relay module in our project functions as a switch to control the locking and unlocking mechanism of the solenoid based on the signals from the ESP32. It provides isolation between the control circuit and the solenoid lock. When the relay coil receives 5 volt, it actuates, powering the solenoid with 9 volts to retract and unlock it. Once the relay is de-energized, the solenoid releases and locks the safe securely. To protect the ESP32 from the relay's inductive load and amplify its GPIO current, we're using a MOSFET transistor. The N-channel MOSFET allows the ESP32 to control the relay indirectly. When the ESP32 sends a high or low signal, it activates or deactivates the MOSFET, which in turn de-energizes or energizes the relay coil.
Here's the layout of our main PCB that has 2 layers with pin headers reserved for the keypad, fingerprint scanner, RGB LED, our buzzer, motion sensor, display, door sensor, and the external USB to UART converter that we'll be using to upload our code.
Our second PCB is a 2-layer board with traces 20 mils thick. It includes components such as 5-volt regulator and a power barrel jack for our power source. Additionally, we will use screw terminal blocks to connect external components such as the solenoid to this PCB and to our main PCB for logic switching.
For the finalized design of our main PCB, 2 modifications were made. The first one was soldering a wire to connect the fingerprint scanner trace and motion sensor trace to 5 volts so that they will receive pressure. The second change was to scratch off an extra pin that we weren't using so that we'll have an extra ground pin that will be used to implement our door sensor stretch goal.
For the finalized design of our locking mechanism PCB, 2 modifications were made. The first one was soldering a 1K resistor to connect the LED indicator to the 5 volts voltage regulator. The second change was to add the signal pin of the relay to an extra pin we weren't using so we can use it to control the flow of the current in the circuit.
The picture in this slide shows the final design of our website. We have a box on the left-hand side where the user can sign up for emails. After the user enters their email in the box and presses the submit button, ESP32 will automatically save their email into its memory and they will receive a registration confirmation email. On the right-hand side, we have a list of emails informing the users which emails they will receive directly from our safe. We have also added a contact info at the bottom, including the SmartSafe email in case they wish to contact us. In this slide, we will discuss the final email notification system. On the left, we are showing how the EEPROM saves the user's email into the ESP32's memory after they enter it from the website. They will then receive an email confirming that they have signed up, which is shown on the right. An example email is shown at the bottom right, informing the user that someone has accessed their safe. The user will also receive additional emails from our safe, which is listed in the previous slide on our website. In addition, they can expect to receive emails from a special Gmail account that was created for this project called smartsafesd1@gmail.com. This shows how the work was distributed among all team members. Eric primarily worked on main PCB development and PCB soldering and fabrication, and assisted with lock PCB development and testing the email web server. Alexis primarily worked on lock PCB development and safe design, and assisted with the main PCB development and PCB soldering and fabrication. Myself, Lakshmi, primarily worked on software code and implementing the email and web server, and assisted with component testing and the safe user interface. Nick primarily worked on component testing and the safe user interface and assisted with software code and safe design.
This table outlines the total cost for the main components of our project and the budget we estimated from Senior Design 1. The largest expense is the power source, as it includes the battery backup system. Additionally, the PCB contributed significantly to the difference between our initial budget and the actual bill of materials due to the higher than expected shipment costs. However, we were fortunate to save money on the housing by receiving free sheet metal. In this table, you can see the timeline of our progress from beginning of Senior Design 2. Implementing Wi-Fi and email was our biggest challenge for software, and trying to fix our STDIO problem on our microcontroller was our biggest hardware challenge. But thanks to everyone's hard work and collaboration, we reached all of our milestones and even finished ahead of schedule.
Thank you for watching our presentation.